significant figures and uncertainty. In chemical processes, we often need to measure variables such as flow rate of a stream, temperature, pressure, time, volume, mass, etc. Responsible scientists and engineers agree that a measurement should include three pieces of information. The magnitude of the variable being measured. Here we are measuring the air flow rate and the magnitude is 150. But it is meaningless if we don't indicate the unit. So therefore, we need to provide the unit of that magnitude as well. For example, liter per minute in this case. And finally, an estimation of this uncertainty or error associated with the variable being measured, which is very important. We need to maintain the proper degree of certainty when you add, subtract, multiply, and divide numbers that implicitly have associated uncertainty. We are using a definition called significant figures to determine the uncertainty associated with our numbers and values. So, significant figure is an indication of the precision with which a quantity is measured or known. The digits from the first non-zero digit on the left to the last digit on the right, if there is a decimal point, and remember whether it is non-zero 0, or the last non-zero digit of the number if there is no decimal point. So you're always first looking for the decimal point in your values or numbers, and then we calculate the significant figures for each of them. Remember, there is no uncertainty with pure integers, the quantities that are known to us. For example, 2 heat exchangers, or 3 pumps, or 3 distillation columns. Let's look at an example together. We have got 4 numbers and we are going to look at the significant figures for each number. So first we have got 12.44. We have got a decimal point. Therefore we're going to count 1, 2, 3, 4, and the significant number is 4. The second number, 53,000, there is no decimal point. So we're going to just only count from the left to the non-zero, to the first non-zero onto the right. So 5 and 3, 2. So the significant number is 2. The third number, if you notice, we have got a decimal point there. So we're going to count it together. 1, 2, 3, 4, 5. And we have the significant number is 5. And the last number, we have got a decimal point, but we have got also 0 onto the right of the decimal point. So we're going to count from the left. 1, 2, 3, 4, 5, 6. And you can see the significant number is 6. There are several methods in establishing a degree of certainty and calculating the error in our calculations. The first one is absolute error. Then there's another method called relative error, and then finally a more complicated method which is called statistical analysis. In this course, we are going to look at the absolute error and relative error. We are not covering statistical analysis. You can go to the textbooks to look at the statistical analysis, and also in second year you will get familiar with that method too. In absolute error method, when you have got numbers with a decimal point, the last significant figure in a number represents the associated uncertainty. And when you have got numbers without a decimal point, remember that trailing zeros do not imply any additional accuracy. When you are multiplying or dividing the numbers, retain in your final answer the lowest number of significant figures. When you're adding or subtracting, remember the result cannot be more precise than any of the quantities added or subtracted. In relative error method, or I would call it common sense, is we have to avoid increasing the precision of our results very much over the precision of our measurements or data that we have gathered. So remember, when you're presenting the results of your calculation, they cannot give the indication the results are more accurate than the where you started with. So let's do an exercise together. We have got measure two quantities, for example, flow rates. One is 1.01 and the other one is 1.09. And we're going to divide these two numbers. So I suggest you take your calculator at this point and divide them and look at the results. We want to present the results in our report, and we have to make sure we are not going to that indication that the result of this division is more accurate than our measurements. Right, now you can see a picture of my calculator, and you can see I've done that. I've divided 1.01 by 1.09, and the number I've got on my calculator is 0.92660555046, and that depends on how accurate is your calculator, or how many depends on how many numbers can be displayed on your calculator. The first method I'm going to use is the absolute error to calculate the uncertainty. So if I do that, you can see here on the we have got 0.9266. I put it there. Then we have to look at the number of the significant numbers for each number, and then we look at the lowest significant figures. So the significant number of the first value, 1.01, is 3, and for the other one is also 3. So the lowest significant figures in this example is 3. Therefore, we have to retain that and in our final answer. So therefore, I have to round my calculated number to 0.927. Now let's analyze the results and look at the absolute error method. If we look at the uncertainty in our calculated result, it'll return 0.1% uncertainty. What we have done is we divided 0.001 by the answer that we returned at 0.027, and that will become 0.001 or 0.1% uncertainty. If we look at the uncertainty of our measurements or the data that we started with, for example, for 1.09, if you look at the uncertainty in that value is 1%. So you can see in the absolute error analysis, we increase the precision or we reduce the uncertainty of the results significantly, and that's wrong. We have to fix it. We have to fix it because we cannot indicate that the final answer is of the calculations is more accurate or precise than where we started, or for example from our measurements. So we are going to use the relative method here, and then I'm going to demonstrate to you. So in the relative method, we have to retain the uncertainty. So looking at the measurements, the uncertainty of our measurements are 1%. Therefore, when we are going to present the final answer, we're going to keep the same uncertainty in our number, and then in this case I'm going to return the number of 0.93, which has got a relative error of 1%. And this is the concept of the relative error, and the decision is really up to you, but always avoid increasing the precision of your results. So to sum up, always avoid increasing the precision of your answers over the precision of your measurements or the data that you have received. This is very important in engineering, and especially when you are doing the measurements, when you are doing the calculation, it sometimes happens. If you are using Excel spreadsheets, remember Excel spreadsheets cannot make decision on the uncertainty or precision. So you have to double check the values that the spreadsheets are returning in your calculations and correct them and fix them, and don't give that indication that the final value of your calculations is more accurate than where you started.